In the output window, we can also see that the three-way interaction, annealing temperature chromium content furnace type, can also be considered significant, with a p-value of 0.019. Three-way interaction plots are not automatically generated as part of a DOE analysis by default like two-way interaction plots, but can be generated with some data management as follows. In precise terms, a separate three-way interaction plot is now generated for each of these 4 operating points in the two-way interaction plot in order to include the third main factor, annealing temperature, in addition to these 4 operating points. To do this, we first need to do some data management with our current dataset. For this, we first close our output windows for more clarity, and take a closer look at the data structure. In this data sheet, our data is in a so-called stacked form. This means that both the possible combinations and the results of our response variables are stacked on top of each other in 16 lines. And it is also easy to see that 8 lines each have the same data structure. This is because the data structure in the data stack from lines 1 to 4 is identical to the data structure of the data stack from lines 9 to 12. In both data stacks, the annealing temperature varies from line to line, the chromium content changes every 2 lines, and the furnace type remains constant with the jacket furnace type level. Whereas the data structure in the data stack, from lines 5 to 8, is identical to the data structure of the data stack, from lines 13 to 16. Again, the annealing temperature varies from line to line in each case. Also, the chromium content changes every 2 lines, and also the furnace type level remains unchanged, but with the difference that here the furnace type level is Conti. Now, to be able to generate our 4 three-way interaction plots, we must first combine all lines with identical data structure. This means that we must first merge datasets 1 to 4 and 9 to 12 into a new dataset with the common group variable, factor level jacket. We combine the datasets 5 to 8 and 13 to 16 into a new dataset with the common group variable, factor level Conti. We do the same again, but now with the common group variable, factor level 900 degrees Celsius, respectively with the common group variable, factor level 1200 degrees Celsius. And this results in 4 final datasets, which always refer to one common factor level. In this unstacked structure, it is then very easy to construct the three-way interaction plots that are of interest to us. We could unstack our columns manually by copying the corresponding lines and merging them into corresponding 4 separate datasets. In order to go this somewhat laborious way, we recommend the function, unstack columns. Here we proceed as follows. We click on Data, and then on Unstack Columns. First of all, we want to unstack the data from the columns embrittlement proportion, annealing temperature, and chromium content. And these are to be unstacked first of all, according to the factor levels of our main factor furnace type. And we therefore enter in the input field, using subscripts in, our main factor furnace type. This unstacked data set according to the furnace type is then to be displayed in a new worksheet called Unstacked by Furnace Type. We confirm our entries with OK, and we receive a new worksheet with the name, Unstacked by Furnace Type, in which the data from the columns embrittlement proportion, annealing temperature, and chromium content, are displayed on the one hand, according to the factor level jacket, and on the other hand, according to the factor level Conti. Now we will again perform the same unstacking, but for the group variable annealing temperature, or rather for its 2 levels 900 degrees Celsius and 1200 degrees Celsius. To do this, we activate our original worksheet, open the last input window with the key combination Ctrl-E, and delete all older entries with the function key F3. This time, in addition to the embrittlement proportion, we now transfer the factors chromium content and furnace type, and transfer into the field using subscripts in, our group variable annealing temperature. And give this unstacking the corresponding designation, unstacked by annealing temperature, confirm our entries with OK, and we receive another worksheet, now with the designation, unstacked by annealing temperature. In this data set as desired, our data are now available unstacked according to the factor level 900 degrees Celsius on the one hand and according to the factor level 1200 degrees Celsius on the other hand. And we can now create the corresponding interaction plots for these 4 datasets as follows. We first activate our worksheet, Unstacked by Furnace Type, click on Statistics, Analysis of Variance ANOVA, Interaction Plot. Transfer our response variable embrittlement proportion jacket, Transfer our corresponding data sets as factors from the columns, annealing temperature jacket, chromium content jacket, and confirm with OK. Thus, we would have our first interaction plot, which refers to the factor level jacket. We open the last input mask with Ctrl-E, delete all older inputs with the key function F3. Next, accept our response variable, embrittlement proportion Conti, with the associated factors, annealing temperature Conti, and chromium content Conti. Confirm with OK and receive our second interaction plot, which refers to the factor level Conti. Next, we activate our worksheet, unstacked by annealing temperature. We open the last input mask again with Ctrl-E, delete again all previous entries with the key function F3. Now accept our response variable, embrittlement proportion at 900 degrees Celsius, with the associated factors, chromium content at 900 degrees Celsius, and furnace type at 900 degrees Celsius. Confirm with OK, and obtain our third interaction plot, which refers to the annealing temperature level, 900 degrees Celsius. We open the last input mask again, with Ctrl-E, delete again all previous entries with the key function F3, now accept our response variable, embrittlement proportion at 1200 degrees Celsius, with the associated factors, chromium content at 1200 degrees Celsius and furnace type at 1200 degrees Celsius. Confirm with OK and obtain our fourth interaction plot, which refers to the annealing temperature level 1200 degrees Celsius. In order to discuss all four interaction plots with regard to each other, we should display all plots side by side. For this purpose, we can use the useful function, Layout tool, which we open as follows. We click on one of our plots, activate with the right mouse button the drop-down menu, and select with the left mouse button the option, Layout tool. We clean up our layout by removing the automatically placed first graph, and then we transfer our four plots with a double click on each interaction plot, and confirm with Finish. For didactic reasons, we also add our original factorial plot at this point. And first start with the interaction plot, embrittlement proportion in percentage jacket. It is easy to see that there are no significant interactions here, because both action lines show an almost parallel course in the same direction. Thus, there is no interaction between the chromium content and the annealing temperature in the batch annealing, because the mean embrittlement proportion basically decreases when the chromium content is increased from 20% to 30%, independent of whether the annealing temperature in the jacket is 900 or 1200 degrees Celsius. The fact that in principle lower embrittlement proportions are produced at 1200 degrees Celsius than at 900 degrees Celsius is very useful for a corresponding technical recommendation for action, but no indication for an interaction. We also find identical progressions with almost identical slopes of action lines in the interaction plot for the factor level Conti annealing. Here too, there are no significant interactions, because the embrittlement proportion basically increases as soon as the chromium content is increased from 20% to 30%, regardless of whether we heat treat at 900 or 1200 degrees Celsius. The remaining two diagrams with clearly recognizable significant interaction effects are now of interest, identifiable by the fact that in both cases the action lines cross in opposite directions. The original interaction plot, chromium content furnace type, also provided us with the information at this point that the lowest embrittlement proportion of 0.8325% in continuous annealing can be achieved with a chromium content of 20%. However, this is without any statement about the mean embrittlement proportion, with an additional dependence on the annealing temperature level. This is because the value of 0.8325 is basically an averaged value from both temperature levels. The expected average embrittlement proportion for a recommended constellation of furnace type Conti and chromium content 20%, as a function of the third factor, now provides us with our two three-way interaction plots at these points. Although both interaction plots provide us also like the original general interaction plot, chromium content furnace type, first of all with the already known information, that with the furnace type Conti, and 20% chromium, the average embrittlement proportion is the lowest. However, at this point we now obtain the important information, that in addition to the Conti furnace type, and a chromium content of 20%, in connection with the specific temperature level of 1200 degrees Celsius, the average embrittlement proportion will be lower than with a temperature level of 900 degrees Celsius, with otherwise the same settings. In precise terms, the embrittlement proportion would increase from 0.78% to 0.885% if instead of an annealing temperature of 1200 degrees Celsius, an annealing temperature of 900 degrees Celsius is set at a reduced level. Thus, behind this original overall mean embrittlement proportion of 0.8325%, according to our two-way interaction plot, are the individual values identified in these three-way interaction plots. For the arithmetic mean of these two single values, 0.78% plus 0.885% divided by 2 results in 0.8325%. This information with this level of detail cannot be directly recognized from the two-way interaction alone. Therefore, it is always beneficial to include these additional differentiated three-way interaction plots in the DOE analysis with some data management. So much for the important interpretations and insights from our factorial plots.